Good morning, everyone. I'm Richa Wason, and today we are going to discuss the topic that is torque on an electric dipole in a uniform two-dimensional electric field. For this topic, basically, we have to know what is electric dipole and uniform two-dimensional electric field. We have already discussed these two topics, and we know that electric dipole is a system in which there are two charges which are separated by a small distance between them. The condition is that these two charges should be equal and opposite. So here you can see this is an electric dipole where we are having two charges minus q and plus q, and they are separated by a small distance d, and this dipole has been placed in an external electric field which is being shown by the arrows. This is the direction of external electric field, and it is having electric field intensity E. So this system is in which we have a two-dimensional uniform electric field. Why can we say that it is uniform? Because you can see that the lines, the arrows which are drawn, they are equidistant from each other. So this shows uniform electric field. And minus q and plus q, they are making a system, and they are having equal charges. Magnitude of them, the charges are equal and their polarities are different. So there are two equal and opposite charges, and they are separated by a small distance d. So this is our dipole. So now we are going to study that what happens when an electric dipole is placed in a uniform electric field. So what happens is that a torque is produced. We know the torque is the rotational effect produced on the body by the force. So here, when a dipole is placed in this uniform electric field, the two charges, they experience forces, and these forces produce torque on the dipole, and this torque produces a rotational effect in the dipole along the direction of the uniform electric field. So now let's study what will be the formula, what will be the derivation of this torque, and how will we derive it. So here we will consider an electric dipole, which is again, it is the two charges which are having same magnitude but opposite sign, that is minus q and plus q. They are separated by small length, the distance 2l between them. So the dipole moment, which is denoted by P, will be, we know that the dipole moment is magnitude of any charge multiplied by the distance between the two charges. So this will be the dipole moment which will be produced by this dipole. And what is the direction of the dipole moment? It is always from negative to positive. So the direction of dipole moment will be negative to positive. Now here you can see that we are taking this dipole in such a way that it is making angle theta with our electric field intensity. This E is the electric field intensity. The arrows, the parallel lines which you are seeing, these are the electric field lines, and as they are equidistant, so we will say that E is uniform. And as we are considering it in a plane, so it is, and we know that plane is a two-dimensional figure, so here E is two-dimensional also. So now again let's move on to diagram. We can see there is a uniform electric field, and we have placed a dipole in this electric field which is making angle theta with the direction of the electric field. Now what will happen is that because of this electric field, the dipole The two ends of the dipole which are having our charges plus q and minus q, they will experience electrostatic force. This force will be experienced by both the charges. Now, what will be the direction of this electrostatic force and what will be its magnitude? Let's discuss that. So first of all, let us take charge plus q. So this plus q charge is experiencing a force due to this uniform electric field, and we have already studied that the positive charge experiences the force in the same direction as that of the electric field. So if we say that electrostatic force F1 is on charge plus Q, then F1, we know by formula that the electrostatic force will be equal to the product of the charge and the electric field intensity. So the magnitude of the electrostatic force experienced by the positive charge will be QE, and its direction will be the same as that of electric field lines. Now we come to our second charge, that is minus Q. So this minus Q charge will also experience electrostatic force due to this uniform electric field, but as it is minus, so its electrostatic force will be in the direction opposite to the direction of the electric field intensity or the direction of the electric field. So we can say that if F2 is the electrostatic force on minus Q charge, then F2, again it is equal to the product of the charge and the electric field intensity, and its direction will be opposite to that of electric field E. So in this diagram, you can clearly see the directions of forces F1 and F2. These forces are equal in magnitude. Their magnitude is same because the magnitude of charges is same and electric field in which they are kept is also same. So the magnitude of electrostatic forces will be same, but their directions will be opposite. So what will be the net force? So net force on the dipole, that will be equal to F1. It will be vector sum of these two forces, and as they are opposite in direction, so they will cancel out each other and we will get QE minus QE, and that is 0. So the net force on the dipole when it is placed in a uniform electric field will be 0. Why? Because the forces experienced by these two charges will be equal in magnitude, but they will be opposite in directions. So that means these forces will not produce any translational effect on the dipole. That means the forces will not produce any translatory or translational effect on dipole. What does this mean? This means that forces will not be able to displace the dipole from its position. They will not be able to move it in any of the directions. The dipole will be stationary at its point, right? So the forces which are acting on the 2 points of the dipole, they are equal and opposite in direction. So their net force is 0. So there will be no displacement of the dipole in any of the directions. Then what will happen? We can again see the diagram. These forces are equal and opposite, but their line of actions are totally different. That means one force is along this line of action and the other force is along this line of action. So their line of actions are totally different. So here these two forces will make a couple. These forces will make a couple. When do we get a couple? When the forces are equal and opposite to each other, but their line of action are totally different. Their line of action are not same. For example, if the force F1, which is equal to QE, was having this line of action and the force F2 was also having the line of action like this, then these forces would have cancelled out each other and there was no couple. No couple would have found, right? Why? Because their line of action is same. But in the case of dipole, when it is placed in uniform electric field, the direction, the line of actions of the two forces, one is this one and the other one is, let me just show you. The line of action of F1 is this and the line of action of F2 is this. So these two forces, they will cancel out each other in magnitude, but as their line of actions are opposite, so they will form a couple. And you have already studied about couple in class 11th. When a couple is formed, then these forces, these electrostatic forces will produce rotational effect in the dipole. What does this mean? This means that the dipole starts rotating like this. It will start rotating like this, like a wheel. The dipole will be stationary on its position. It will not move here or there, but what will happen? The two forces will form a couple and they will produce rotational effect in the dipole, and dipole will start rotating about its axis. This is the axis. This is the axis which we are talking about, right? So the dipole will start rotating about its axis in the uniform electric field. So this is what is going to happen. Now, what is the rotational effect? That rotational effect which we are talking about, which will be produced by the couple formed by these two electrostatic forces, that is called torque. So when a dipole is placed in an electric field making an angle theta with our uniform electric field, then the dipole will experience a rotational effect which is called torque, and this rotational effect will be formed by the forces acting on the 2 points of the dipole where its charges are residing. So now we come to know that the why torque will be created on the dipole, right? So we have understood this. Now we have to find out the formula. So we say that let us consider an electric dipole consisting of two equal and opposite point charges minus q and plus q at point A and point B. They are separated by a small distance to L. Okay. So now the dipole moment which will be produced will be equal to, this will be equal to, the magnitude of dipole moment will be equal to q into 2L. Let this dipole be held in a uniform electric field at which is having electric field intensity E, and the dipole is making an angle theta with our electric field. Now the forces which are acting on the dipole will be force at plus q will be equal to q into E, which will be along the direction of the and force at minus q will be equal to minus QE in a direction opposite to electric field. Now we want to find out the expression, and we know that torque is denoted by this sign which is called tau. So tau is equal to any of the forces which are acting into the perpendicular distance. So we have to find out, we know that the force which is acting is QE, the amount of force is equal. But now we have to form the perpendicular distance, and this perpendicular distance will be the arm of couple. So we will see that the arm of the couple which is forming here, let us consider it now. Now you have to see that this is the axis. So the arm of the couple which we are talking about, this is the axis, this is the force. If we take the upper force, that is F1, then the perpendicular distance between this axis, just imagine this is the axis coming towards you and the force is going in the west direction, then the axis will be at perpendicular distance to the force. This will be the perpendicular distance, right? So if this part is L and this part is also L, we can divide this total length 2L into two parts, L and L, because theta is this point, this axis of rotation will be considered as the center of the dipole. So from here we will get torque on plus Q, or torque due to F1 will be equal to the magnitude of the force, which is QE, into the perpendicular distance. So here this angle is theta and this part is L. So if we resolve this L into two rectangular components, we get it that this side will be L cos theta and this side will be L sin theta, this side. So the perpendicular distance which we are talking about, the perpendicular distance or arm or couple which we are talking about is L sin theta. So torque becomes QE into L sin theta. Let us say this is because this is torque due to force F1, let us say this is torque 1. And if you see, we can also write it as QE L sin theta, because this is sign of multiplication. Now we come to second torque, that is due to torque due to F2. So when we talk about the force which is F2, here the torque will again be the force into perpendicular distance. So again we calculate, force will be same, the magnitude is QE, right? And the perpendicular distance, here we will see that L is the perpendicular, we are talking about this arm L, this is the part which we are talking about. So this, if we talk about this part, then this L again it is making angle theta with our direction of electric field. So we will again resolve this L into two components. One is our L cos theta, which will in this direction, and the other one will be L sin theta. So we have to consider the perpendicular distance, so it will be this portion. This is L sin theta. So here torque, let us say this is torque 2. So torque 2 will be QE into L sin theta. So we have got two torques now, tau 1 and tau 2. Now we know that the total torque on the system will be sum of these two torques. So total torque, that will be tau 1 plus tau 2. Now we have to consider directions also, because it is a vector quantity. So if we consider the directions, then tau 1, if we see this tau 1 which is acting, which is due to F1, its direction will be like this. because it will be moving dipole in this direction. So we will say tau 1 is clockwise. And if we see this torque 2, if we talk about torque 2, it is producing this effect like this. This is tau 2, this is tau 1. So this is also clockwise. So as both are clockwise, so they will add up and we will get QEL sine theta plus QEL sine theta. So we get QE 2QEL sine theta. So this is the total torque which will be produced, right? Now we can also write it like this. Torque is equal to Q into 2L E sine theta. Why have we written it like this? Because we know that the dipole moment is equal to Q into 2L. So we will replace this Q into 2L by the dipole moment. So it will become P E sine theta. So from here we come to the expression for the torque. Because it is we are talking about the magnitude only, so we will not put a vector sign. It will be torque is equal to Pe sine theta, and in vector form we know that P is a vector form, vector physical quantity, and E is also vector physical quantity. So their sign, their product will be a cross product. So now in vector form it can be written as tau is equal to P cross E. So this is the formula for torque produced in a dipole when it is placed in a uniform electric field. Here you can see that the torque is resultant of the cross product of P and E. So we have to see its direction as well. So now if we talk about the direction, then here you can see if P, we have taken P is in this direction, that is minus Q is here plus Q is here. So direction of the dipole moment is always from negative to positive. So it is in this direction and E is in this direction. So now we want to find out direction of torque. Now this theta is the angle between the dipole moment and electric field intensity. So from here you can say that we will find out the direction when P is moving along E. When the dipole, the direction of the torque will be same in which the dipole is moving, right? So direction of torque will be same as that of the dipole. So earlier I have told you that dipole is moving in clockwise direction. So here you will see that the torque will be also in the same direction. That means downwards. It will be downwards. How can we always point out what will be the direction of the torque? So it is given by the formula or by right hand thumb rule. So you have already studied in class 11th that the resultant vector of a cross product between two physical quantities. Which physical quantity? Vector physical quantities. Is always perpendicular to the plane in which these vectors are present, right? And If we talk about right hand thumb rule, how will it help in us in finding out the direction of the torque? Then we will consider the curling of fingers in the plane in which our vectors are kept. So as you can see in this diagram, P and E, they are kept in the XY plane. You can see they are kept in XY plane. This is XY plane. Let us say this is Y axis, this is X axis, because we are considering a two-dimensional electric field. So they are in XY plane. So their torque, their resultant, which is torque, will always be in Z axis, along Z axis. Why? Because it is the rule of cross product that the resultant of cross product will always be in the plane which is perpendicular to the plane in which the parent vectors are present. So we have come to a conclusion that torque in this case will be torque in the given case will be along Z axis. So we have come to this conclusion that torque is in the Z axis. Now whether it will be upwards, it will be coming towards you, or it will be going away from you, that we have to see. So in that case, if we talk about right hand thumb rule, then if the curling of fingers, that is from P to E, if the curling of fingers is in the anti-clockwise direction, you can see yourself, if you take your right hand and you curl your fingers in the anti-clockwise direction, then the torque will be upwards. Okay, so Z axis upward, positive Z axis, the torque will be along the positive Z axis. But if your vectors P to E, as in this case, you can see when we are moving from P to E, the curling of fingers is clockwise and our thumb is pointing in the downward direction. So the downward direction of thumb is giving us the direction of the torque. So in the given case, in the diagram which we are discussing, P is when we are curling our fingers. This curling of finger is showing that we are moving from of our right hand, right? The curling of finger is showing that we are going from P to E, and that is clockwise, and the direction of thumb, that is going downwards. So it is showing that our torque is going downwards, as it is clear in this diagram also. So torque will be along Z axis. It will always be along the plane which is perpendicular to the plane containing P and E, and it will be either upwards or downwards depending on the curling of fingers of your right hand thumb. If the curling of finger is in the clockwise direction, so our thumb will point downwards, and the direction of thumb will give us direction of torque. And this curling of fingers is showing that we are moving from P to E. So in this way, you can find out the magnitude, that is torque is equal to P E sine theta, or we can say torque is equal to P cross E, and we can also find out the direction by right hand thumb rule. So this is all about torque. Now we will also see that there are some values of torque. These will be the special cases if we talk about. So in special cases, the torque can have maximum value and minimum value. So now we will see that when the torque will have maximum value and when will it have minimum value. So if we talk about the special cases, then when this is our electric field right? And if we see that torque is our dipole is perpendicular to the direction of our electric field. In this case, the theta angle becomes 90 degree. And we know that torque is equal to P E sine theta. So here we will put P E sine 90 degree. And when we put sine 90 degree, we know that sine 90 degree is equal to 1. Sine 90 degree is equal to 1. So torque is equal to PE. This is the maximum value which a torque can have. So the maximum value of torque is P into E. And when will this happen? When dipole is perpendicular to electric field, then our torque will have maximum value. That means it will produce maximum rotational effect and it will try to align the dipole in the direction of the electric field. Now we talk about the okay. So now we have talked about maximum value. So it comes out to be maximum value of tau is equal to PE when P is perpendicular to E. Now we talk about minimum value. So minimum value of torque will be when sine theta will have minimum value. And what is the minimum value of sine theta? That is 0. So when our torque is either in the direction of electric field, that is like this, the direction of torque will be, the direction of dipole is minus q2 plus q, so it is also the P is in the direction of electric field. So here we will say the angle between the electric field and dipole, that angle is 0, right? So if we put torque is equal to P E sine theta, so here P E sine 0 will be equal to, it will be equal to 0. Why? Because sine 0 is 0. So we will say that torque will be minimum when P is parallel to E. First is this case. Then if our P is, let us draw the diagram again. If our dipole is anti-parallel, that means it is opposite. Here we have plus q and here we have minus q. So the direction of the dipole moment is opposite to that of electric field. So P is opposite to E. P is opposite to E. Let me write it like this. Then what will happen? We know that sine, we are talking about the minimum value. So we know that when our P is parallel or it is anti-parallel to our electric field, then sine 180 degree is also equal to 0, right? Sine 180 degree is also 0. So torque will be P E sine 180 degree, right? And again it will be 0. So minimum value of torque, we will get minimum value of torque which will be equal to 0. And when will it happen? When P is either parallel to E or P is anti-parallel to E. then we will have maximum and minimum value of torque. Okay. So now we come to two cases, that is stable equilibrium and unstable equilibrium. We already discussed that there will be two cases when torque is minimum. First is when the dipole is parallel to the electric field intensity, and the second case is when the dipole is anti-parallel to the direction of the electric field intensity. So when let us discuss the first case, that is stable equilibrium. We have already studied about the equilibriums in class 11th, and we know that stable equilibrium is that in which when we move any body from that stable equilibrium position, it will again come back to its original position. So here you can see that when the dipole is in the direction of electric field, when the dipole is in the direction of electric field, then the the dipole will be called stable, in stable equilibrium with the electric field. That means the angle between them, for stable equilibrium, the angle between dipole and electric field should be is 0 degree, right? When the dipole is in the direction of electric field, so whatever work we do to displace the dipole from its position, it will directly come back, it will quickly come back to its original position, and it will align itself in the direction of the electric field. Then for unstable equilibrium, if the dipole is anti-parallel to the direction of electric field, that means the dipole is in the opposite direction, the dipole moment is in the opposite direction to that of the electric field, then we say that dipole is in unstable equilibrium. Why? Because here we have to align the dipole in the direction of electric field. So here electric field is very smart. What it wants? Why all these things are being done? Why a torque is acting on the dipole? Because electric field wants to align dipole direction. So this is what electric field wants. Electric field wants to align dipole in its direction. So that is why all these things, all the torque is being produced, the forces are acting on the body, on the dipole, because the dipole is not aligned in the direction of electric field. So when it is aligned in the direction, then electric field is happy. It will not do anything, and the dipole will be in the stable equilibrium with the electric field. But when the dipole is not aligned, that means if it is anti-parallel to the electric field, then what will happen? The field will start producing a torque, and it will try to align the dipole in its direction. And in that case, we will say that dipole is in unstable equilibrium with the electric field. So for unstable equilibrium, dipole and electric field have an angle of 180 degree. So these are the cases when if it is asked that when the dipole is in stable equilibrium with the electric field, so your answer should be that the angle, then the angle between the dipole moment and electric field is 0. That means when the dipole is aligned in the direction of electric field, then the dipole is in stable equilibrium with the electric field. And if the dipole is in direction opposite to the electric field, then it will be in unstable equilibrium with the electric field. Today we discussed about what is dipole. We also discussed what is a uniform electric field. Then I told you what is torque. Then we discussed what will be the formula for the torque. and we came to the conclusion that the formula for the torque is P E sine theta, where P is the dipole moment of the dipole and E is the electric field intensity, and theta is the angle, the acute angle between the dipole and the electric field. Then we also discussed that what will be the direction of the torque. So the direction of torque will be given by right hand thumb rule, and it will follow the rules of cross product. Then we discussed that what will be the maximum value of the torque and what will be the minimum value of the torque. So minimum value of torque is 0 when the dipole is parallel or anti-parallel to the electric field, and maximum value of torque is equal to the product of the magnitudes of dipole moment and electric field, and this happens when P is perpendicular to electric field. Then we also discussed what is stable equilibrium, when we will call the torque the dipole to be in stable equilibrium with the electric field, and when the dipole is said to be in unstable equilibrium with the electric field. So this is all about the dipole when it is placed in a two-dimensional uniform electric field. So thank you so much, and I will just sum up my video here, and for the next topic, that is torque in a non-uniform electric field, I'll make another video. Thank you.